Every packet tells a story, and this course teaches you to read it. The current CCNA 200-301 version 1.1 exam gives you 120 minutes and organizes the blueprint into 6 weighted domains. IP connectivity receives 25%. Network fundamentals and network access each receive 20%. Security fundamentals receives 15%. And IP services plus automation and programmability each receive 10%. Those percentages are guidance, rather than guaranteed question counts, but they tell you where practice matters most. When Cisco says configure and verify, you must know commands, interpret output, and troubleshoot a result. When Cisco says interpret, explain, describe, compare, or recognize, you still need conceptual precision, but configuration practice deserves extra attention. We will follow that weighting order and repeatedly connect configuration to verification, because accepted syntax is never proof that a network works. Begin with the routing table by entering show IP route in privileged exec mode. A route such as 010.10.10.0/24(110/20) via 192.168.1.2 contains a source code, destination prefix, administrative distance, metric, next hop, and outgoing interface. The code L identifies a local interface address. C identifies a connected network. S identifies a static route. O identifies OSPF. And OIA identifies OSPF interarea. You should also recognize D for EIGRP, R for RIP, B for BGP, and S star for a static candidate default. A connected entry describes a network attached to an interface, while a local entry normally describes that interface exact/32 IPv4 address. The router compares the packet's destination address with routing prefixes through binary matching rather than choosing a vaguely similar network. Administrative distance chooses between route sources that offer the same prefix. Connected routes have distance 0. Static routes normally have distance 1. EIGRP, internal routes have distance 90. OSPF routes have distance 110, and RIP routes have distance 120. You should also recognize eBGP, distance 20, and IBGP, distance 200. A metric compares paths learned by one routing protocol, so RIP uses hop count, OSPF uses cost, and EIGRP uses a composite metric. Never compare an OSPF metric of 10 directly with an EIGRP metric of 30 and declare OSPF the winner, because different sources compete through administrative distance first. A gateway of last resort normally corresponds to 0.0.0/0, and it is used only when no more specific route matches. Route selection always begins with longest prefix match. A destination of 10.1.1.200 can match 10.0.128/16, 10.1.128/25, and the default route. The /25 wins because it fixes the greatest number of destination bits. This rule means an OSPF/24 beats a static /8 for matching traffic, even though static routing has the lower administrative distance. Administrative distance matters only after candidate routes have the same destination prefix length. If an EIGRP and OSPF route both describe 172.16.1.0/24, EIGRP wins because 90 is lower than 110. If two OSPF routes have equal prefixes and distance, the lower OSPF cost wins. Equal cost paths may be installed when every earlier comparison ties, so memorize the order as longest prefix, lowest administrative distance, then lowest metric. Configure a basic IPv4 network static route on R1 with IP route 192.168.2.0.255.255.255.255.10. This instruction sends traffic for 192.168.20.0/24 toward next hop router 10.0.12, verify installation with show IP route, narrow the view with show IP route static, test reachability with ping 192.168.20.1, and reveal the path with trace route 192.168.20.1. Configure an IPv4 default route with IP route 0.0.0.0, 0.0.0, 10.0.12.2. And remember that this route is the least specific fallback. Configure the equivalent IPv6 default with IPv6 route /02001 db8-12-2. Verification must include the table and the data path, because a route can be present while a return route, interface, or policy still prevents communication. A host route selects one exact destination. Configure an IPv4 host route with IP route 192.168.255.255.255.255.255.255.255.255. Dir. An IPv6 host route uses a /128 prefix, such as 2001-db8/100/128. A floating static route provides backup service by using a higher administrative distance than the primary route. If OSPF supplies 172.16.0.0/16 with distance 128, configure the backup with IP route 172.26.16. The static route remains inactive, while OSPF is available and enters the table when the primary route disappears. Verify normal and failed states with show IP route 172.16.0.0 and restore the primary path before declaring the workflow complete. Static routes can identify a next hop, an exit interface, or both. The command IP route 10.20.0, 255.255.0192.168.1.2 identifies only the next hop. The command IP route 10.20.0, 255.255.0.0, serial 0/0/0 identifies only the exit interface. The fully specified command IP route 10.20.0, 255.255.0. Understand what resolution each form requires instead of memorizing syntax without context. After configuration, inspect the selected route, ping a destination, trace the forwarding path, and verify a return path from the far side. If the route does not install, check interface state, address correctness, recursive next hop reachability, and whether a more relevant route appears in the table. Single Area OSPF version 2 is a link state interior gateway protocol that uses cost, administrative distance 110, and IP protocol 89. OSPF does not use TCP or UDP. Start the process with router OSPF1. Assign a stable identity with router-ID 1.1.1. Activate the point-to-point subnet with network 10.0.12.0.0.0.0.3 area 0. and activate the local LAN with network 192.168.1.0.0.0.255 area 0. The process ID has local significance, so a neighbor can use router OSPF 500 and still establish adjacency. The wildcard mask inverts a subnet mask, making 255.255.255.0 become 0.0.0.255 and 255.255.255.252 become 0.0.0.3. A 0 wildcard bit must match, while a 1 wildcard bit may vary. OSPF chooses a router ID by preferring a manually configured ID, then the highest loopback address, and then the highest active physical interface address. And the router ID is a 32-bit value and need not be a reachable host address, but it must be unique in the OSPF domain. A changed router ID may require process restart before taking effect, so verify the active identity rather than trusting the running configuration alone. Suppress unnecessary hello packets on user LANs by entering passive-interface gigabit Ethernet 0/1 under the OSPF process, while still advertising that connected network. You can instead establish a safe baseline with passive-interface default and restore adjacency only on the routed link with no passive-interface gigabit Ethernet 0/0. Verify protocol parameters and advertise networks with show IP protocols, and verify interface-specific OSPF operation with show IP OSPF interface. OSPF routers use hello packets to discover neighbors and move through down, init, two-way, xstart, exchange, loading, and full states. Use show IP OSPF neighbor to inspect neighbor identity, priority, state, dead time, address, and local interface. A full state means required link state databases have synchronized. On broadcast Ethernet, Draughter routers can remain two-way with one another, while each forms full adjacencies with the designated router and backup designated router. That behavior is normal, rather than evidence of failure. Use show IP route OSPF to inspect learned routes and show IP protocols to confirm process settings. When adjacency fails, compare area, subnet, hello and dead timers, authentication, router IDs, interface state, OSPF activation, and maximum transmission unit. A neighbor stuck during database exchange can point toward an MTU mismatch. Point-to-point OSPF networks connect only two routing participants and do not need a designated router election. Broadcast Ethernet can contain many routers, so OSPF elects a designated router and backup designated router to limit full adjacencies. The election prefers highest OSPF, interface priority, and then highest router ID. Default priority is 1, while priority 0 prevents an interface from becoming designated or backup designated. Elections are non-preemptive, which means a later router with better priority does not automatically remove the current designated router. OSPF cost conceptually equals reference bandwidth divided by interface bandwidth, and a route's total cost sums outgoing interface costs along the path. Lower cost is preferred. Verify the network type, cost, timer values, priority, and role with show IP OSPF interface. Then compare that evidence with show IP OSPF neighbor and show IP route OSPF. First hop redundancy protects hosts from losing their configured default gateway. Multiple routers present one virtual IP address, such as 192.168.10.1, and hosts use that stable address instead of a physical router address. HSRP is a Cisco protocol based on active and standby roles. VRRP is standardized and uses master and backup terminology. GLBP is a Cisco technology that can add load balancing to gateway redundancy. If the active forwarding device fails, another router takes over the virtual identity without requiring hosts to change gateway configuration. A second router by itself does not solve the problem unless the devices participate in an FHRP. For exam questions, identify the virtual gateway, active forwarding role, backup role, and failure behavior rather than assuming ordinary routing automatically protects the host's first hop. Network fundamentals begins with device roles. A router connects different IP networks, forwards by destination IP address, and separates broadcast domains. A Layer 2 switch forwards Ethernet frames by MAC address inside a VLAN, gives each port a separate collision domain, and treats each VLAN as a broadcast domain. A Layer 3 switch combines switching and routing and commonly routes between VLAN interfaces. A next-generation firewall adds application awareness, user awareness, deeper inspection, threat detection, and content controls to stateful IP, port, and protocol enforcement. An intrusion prevention system operates inline and can block malicious traffic, while an intrusion detection system primarily detects and alerts. An access point bridges wireless clients into a wired LAN. A controller centralizes policy and management. Endpoints consume services, and servers provide services such as DNS, DHCP, web, file, authentication, email, and applications. Power over Ethernet carries data and electrical power over Ethernet cabling. The switch supplying power is the power sourcing equipment, while the receiving access point, phone, or camera is the powered device. A two-tier campus combines distribution and core functions into a collapsed core above the access layer, which fits many smaller enterprises. A three-tier design separates access for endpoints, distribution for aggregation and policy, and core for fast, resilient transport. A data center spine leaf design connects every leaf to every spine, supporting predictable latency, high bandwidth, equal cost multipath, and east-west traffic. Leaves normally do not connect directly to other leaves. A wide area network links geographically separated sites, while a SOHO appliance often combines routing, switching, wireless, firewall, NAT, and DHCP. On-premises infrastructure is locally operated, while cloud service models include infrastructure, platform, and software as a service. Copper unshielded, twisted pair Ethernet is inexpensive, easy to install, and capable of carrying PoE, with a typical maximum channel distance of 100 meters. Copper has shorter reach and greater electromagnetic interference sensitivity than fiber. Multimode fiber has a larger core and commonly supports shorter building or data center links with lower cost optics. Single-mode fiber has a very small core and commonly supports long campus, WAN, or provider distances. Actual reach depends on the optic and Ethernet standard. Old Hub Ethernet created a shared collision domain, while modern, switched Ethernet normally provides a point-to-point full duplex link. Full duplex eliminates Ethernet collisions on a correctly operating link. Media selection must account for distance, bandwidth, environment, connector, transceiver, and power needs, rather than relying on one simplistic copper versus fiber rule. Troubleshoot physical and data link symptoms with show interfaces and summarize link state with show interfaces status. Examine CRC errors, input errors, output errors, collisions, late collisions, drops, speed, and duplex. A full duplex endpoint connected to a half-duplex peer can show terrible throughput, late collisions, errors, and intermittent behavior even when the interface reports up and up. Modern links often auto-negotiate speed and duplex, but a damaged cable or negotiation problem can reduce a gigabit link to 100 megabits per second or prevent operation. Confirm both ends instead of changing one side blindly. Use show interfaces Gigabit Ethernet 0/1 for focused counters, clear or note a baseline when appropriate, generate test traffic, and check whether counters increase. Physical up status proves carrier, not healthy delivery. TCP is connection-oriented and provides sequencing, acknowledgements, retransmission, ordered delivery, and flow control. Its three-way handshake proceeds through SYN, SYNAC, and ACK. HTTP, HTTPS, SSH, and FTP commonly use TCP because their sessions benefit from reliable ordered transport. UDP is connectionless and omits built-in retransmission and sequencing guarantees, which reduces overhead. DNS, DHCP, NTP, and real-time voice or video commonly use UDP, although application design can use other choices. Do not say UDP is always faster, because observed performance depends on application behavior, loss, congestion, and recovery. When troubleshooting, identify source and destination addresses, transport protocol, source and destination ports, session state, and whether the application implements its own reliability. IPv4 contains 32 bits, and prefix length identifies network bits. For 192.168.10.25/24, the mask is 255.255.255.255. The network is 192.168.10.0. The broadcast is 192.168.10.255, and traditional usable hosts run from .1 through 254. A /25 contains 128 addresses. A /26 contains 64. A /27 contains 32. A /28 contains 16. A /29 contains 8. And a /30 contains 4. Traditional usable counts subtract network and broadcast addresses, although /31 point-to-point links and /32 host routes are exceptions. The address count equals 2 raised to the number of host bits. Practice deriving boundaries instead of depending on a memorized table alone. Use block size to subnet quickly. For 172.16.10.77/26, the mask is 255.255.255.192, and the changing octet block size is 256-192, or 64. Subnets begin at 0, 64, 128, and 192, so 77 lies in the range from 64 through 127, and traditional usable hosts run from 26 for yo. Memorize the private IPv4 ranges as 10.0.0.0/8, 172.16.0.0/12, and 192.168.0.0/16. The private 172 range ends at 172.31.25.5.25.5, so 172.32.1.25 is not RFC 119.18 private space. IPv6 contains 172.32.2. Remove leading zeros within each group, then compress one longest consecutive run of zero groups with a double colon. The fully expanded IP version 6 example shortens to 2001 DB8 :1 and :: can appear only once in an address. Enable forwarding with IPv6 unicast-routing. Enter the interface with interface G0/0. Assign the address with IPv6 address 2001 DB8-1/64 and activate it with no shutdown. Verify status and assigned addresses with Show IPv6 Interface Brief. Inspect the complete interface details with Show IPv6 Interface Gigabit Ethernet 0/0 and inspect routes with Show IPv6. Test a neighbor or remote destination with ping 2001 DB8-1/2 and confirm both forward and return reachability. Global unicast IPv6 space is generally represented by 2000/3 and is routable like public address space. Unique local space is FC00/7, with locally assigned addresses commonly beginning with FD. Link local space is FE80//10 and is essential for neighbor discovery, routing protocol communication, and IPv6 next hops, but routers do not forward link local traffic beyond the link. Multicast begins with FF00/8, and IPv6 uses multicast rather than broadcast. Anycast places the same address on multiple devices and lets routing select the topologically closest or best routed instance. Modified EUI64 can form a 64-bit interface identifier by inserting FF/FE into a 48-bit MAC and flipping the universal local bit. These categories answer scope and forwarding questions, so identify type before diagnosing reachability. Client troubleshooting starts with local configuration evidence. On Windows, use ipconfig. Expand details with ipconfig/all. Inspect routes with routeprint. Inspect ARP with ARP-A. Test with ping, and trace with tracert. On Linux, use ipedr, iproute, ipnae, ping, and traceroute. On macOS, use ifconfig, netstat-rn, route-ngetdefault, arp-a, ping, and traceroute. Always check address, prefix or mask, default gateway, DNS server, and DHCP status. Compare the client's subnet with its gateway before testing a remote service. A successful ping to the local gateway isolates many local issues, while failure by name after success by address points toward DNS rather than routing. Wireless fundamentals begin with the SSID, which identifies a WLAN but provides no security by itself. In common North American 2.4 GHz deployments using 20 MHz channels, channels 1, 6, and 11 avoid overlap. 5 GHz offers more usable channel choices. Radio performance changes with distance, walls, metal, neighboring Wi-Fi, Bluetooth, interference, channel width, and transmit power. WP is obsolete. WPA is legacy. WPA2 remains strong when correctly configured, and WPA3 is newer and stronger. Server virtualization runs multiple guest operating systems through a hypervisor, while containers generally share the host kernel and are lighter. Virtual routing and forwarding creates separate routing tables on one router, allowing isolated contexts and even overlapping address ranges. Ethernet switching begins by learning the source MAC address on the ingress port. The switch then looks up the destination MAC address in the table. A known unicast frame is forwarded only through the matching port, while an unknown unicast is flooded through other ports in the same VLAN. A broadcast destination of FF, FF, DAF, FF, 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 FF is also flooded within that VLAN except through the incoming port. Dynamically learned MAC entries age out after inactivity, commonly around 300 seconds on Cisco switches. Remember the sequence as learn source, inspect destination, forward known traffic, and flood unknown or broadcast traffic. Use show MAC address table to verify learning, and use show MAC address table dynamic to focus on dynamic entries. The observed VLAN and port should match the physical path. Network access starts with VLAN creation and assignment. A VLAN is a logical Layer 2 broadcast domain, so devices in different VLANs require Layer 3 routing to communicate. Create the user VLAN by entering VLAN 10, and optionally assign a descriptive name with name accounting. Enter the endpoint port with interface G0/1. Force access behavior with switch port mode access, and assign membership with switch port access VLAN 10. Verify the VLAN database and port assignment with show VLAN brief. Then inspect operational and administrative switch port properties with show interfaces switch port. If a host remains disconnected, check physical state, access mode, assigned VLAN, VLAN existence, spanning tree state, and client addressing. Do not treat the default, native, and management VLANs as interchangeable concepts, even when all happen to use VLAN 1 in a default configuration. A voice VLAN allows an IP phone and attached computer to share one physical switch port while separating traffic. On the port, use switch port access VLAN 10 for ordinary computer data and switch port voice VLAN 20 for phone traffic. Keep switch port mode access configured because this is an edge port rather than an ordinary interswitch trunk. Verify the resulting access and voice assignments with show interfaces switch port, and confirm both VLANs exist with show VLAN brief. The default VLAN is VLAN 1 on Cisco switches. The native VLAN classifies normally untagged traffic on an 802.1q trunk, and the management VLAN carries device management traffic by design. Their purposes remain distinct, and secure designs usually avoid casual dependence on VLAN 1. Router on a stick provides inter-VLAN routing over one physical trunk. Keep the physical router interface active, then enter interface G0/0.10. Identify VLAN 10 with encapsulation.1q10, and assign its gateway with IP address 192.168.10.1.255.255.255.0. Enter interface G0/0.20. Identify VLAN 20 with encapsulation.1q20, and assign IP address 192.168.20.1.255.255.255.0. Configure the connected switch port as a trunk, and permit both VLANs. Verify sub-interface status with show IP interface brief. Inspect connected routes with show IP route connected. Verify the trunk with show interfaces trunk, and test between correctly addressed hosts. A failed workflow commonly points to an absent VLAN, wrong tag, shut physical interface, disallowed VLAN, or incorrect host gateway. A multi-layer switch can route with switched virtual interfaces. Enter interface VLAN 10 and assign IP address 192.168.10.1.255.255.255.0. Then enter interface VLAN 20 and assign IP address 192.168.2.0.1.255.255.255.0. Enable Layer 3 forwarding with IP routing. Activate each SVI with no shutdown when necessary, and ensure each VLAN exists with at least one operational participating port so the SVI can come up. Verify interface state with Show IP interface brief. Verify connected networks with Show IP route connected, and test gateway reachability from each VLAN. Router on a stick centralizes gateways on router subinterfaces, while SVI routing commonly provides higher performance inter-VLAN routing inside an enterprise switch. An 802.1q trunk carries multiple VLANs over one physical link. Enter the uplink with interface G0/24 and force trunking with switch port mode trunk. Change the native VLAN with switch port trunk native VLAN 999 and restrict carriage with switch port trunk allowed VLAN 10, 20, 30. Both ends should agree about trunk mode, native VLAN, and allowed VLANs. A native VLAN mismatch can misclassify untagged traffic, create connectivity failures, and trigger spanning tree warnings. A VLAN absent from the allowed list cannot cross that trunk, even if it exists on both switches. Verify operational trunking, native VLAN, and allowed and forwarding VLANs with Show Interfaces trunk. Then compare both ends before changing routing. CDP and LLDP discover directly connected devices at Layer 2. CDP is Cisco proprietary, and Show CDP Neighbors reveals a concise neighbor table, while Show CDP Neighbors Detail can reveal device name, local interface, remote interface, platform, and IP information. LLDP is vendor neutral, and Show LLDP Neighbors provides its concise table, while Show LLDP Neighbors Detail provides expanded information. Neither protocol discovers an entire routed path, so use them to validate the immediate physical neighbor and cabling relationship. If the expected neighbor is missing, verify protocol operation, local interface state, and peer support. Do not replace proper inventory or routing verification with a discovery protocol assumption. Ether channel bundles compatible physical links into one logical port channel, increasing bandwidth and redundancy while presenting one logical link to spanning tree. LACP uses active and passive negotiation modes. Active with active forms, active with passive forms, and passive with passive does not form. Enter the members with interface range G0/1-2. Then add them with channel-group 1 mode active. Enter the logical interface with interface port-channel 1 and configure switch port mode trunk there. Verify bundling with Show Ether Channel Summary, where flags should show the port channel in use, and member ports bundled. Also verify trunk properties with Show Interfaces trunk. If formation fails, compare speed, duplex, access VLAN, trunk mode, native VLAN, allowed VLAN list, and channel group settings across members and peers. A Layer 3 Ether channel carries routed traffic instead of switched VLAN traffic. Enter interface range G0/1-2. Convert members with no switch port, and negotiate them with channel-group 1 mode active. Enter interface port-channel 1. Apply no switch port, and assign IP address 10.0.12.1.255.255.255.255. Configure the peer consistently. Then verify with Show Ether Channel Summary, Show IP Interface Brief, and Show IP Route Connected. Ping the peer port channel address to test forwarding. Place configuration on the logical interface wherever iOS expects shared properties. because inconsistent member settings prevent safe bundling. A working logical interface, plus suspended members, is not a successful result, so inspect every member flag. Spanning tree protocol prevents layer 2 loops that otherwise create broadcast storms, MAC table instability, and network collapse. Ethernet frames lack an IP-style time to live, so a loop can circulate frames indefinitely. STP elects the switch with the lowest bridge ID as root. The bridge ID combines bridge priority, a VLAN-related system ID extension, and MAC address. Default priority is 32768. Lower values win, and valid priority steps normally increment by 4096. Make the intended switch route for VLAN 10 with spanning dash tree VLAN 10 route primary, or set an explicit value with spanning dash tree VLAN 10 priority 4096. Verify the actual route and local roles with show spanning dash tree VLAN 10 rather than trusting design intent. Every non-route switch selects one route port based first on the lowest total path cost toward the route, while the route bridge has no route port. Each Ethernet segment receives one designated port, representing the best path toward the route for that segment. On the route bridge, all active STP ports are designated. Rapid spanning tree roles include route, designated, alternate, and backup, while states include discarding, learning, and forwarding. Rapid STP combines older blocking and listening behavior into discarding. Read show spanning dash tree VLAN 10 from the route ID through local bridge ID. Then, inspect each interface role, state, cost, priority, and type. Determine topology from evidence, instead of assuming every redundant interface should forward. PortFast accelerates an edge port's transition to forwarding without disabling STP. On a verified endpoint port, configure spanning dash tree PortFast. Do not use ordinary PortFast casually on switch-to-switch links. Pair edge behavior with BPDU guard by entering spanning dash tree BPDU guard enable, which error disables the port if a BPDU appears where an endpoint should be. Root guard prevents a downstream neighbor from becoming root and is enabled on the protected port with spanning dash tree guard root. Loop guard protects a redundant path from incorrectly forwarding when expected BPDUs disappear and is enabled with spanning dash tree guard loop. BPDU filter suppresses BPDUs and can create dangerous blindness, so do not confuse it with BPDU guard. Verify status with show spanning dash tree inconsistent ports, show spanning dash tree interface detail, and interface status evidence. Cisco wireless networks can use autonomous access points or controller-based lightweight access points. Autonomous devices contain more local management and control, while a wireless LAN controller centralizes major functions at scale. Lightweight APs commonly communicate with a controller through CAPWAP. Local mode normally serves clients. Flex Connect supports remote site designs and can perform local switching. Monitor mode scans radio conditions. Sniffer mode captures traffic. Rogue detector mode helps find unauthorized access points. And bridge or mesh modes provide wireless bridging. A client reaches an AP by radio. The AP connects to an access switch by Ethernet and often PoE, and controller connectivity can involve trunks, link aggregation, and multiple VLANs. Interpret roles and traffic paths rather than memorizing one universal wiring diagram. Management access methods differ in security and placement. Console access provides local out-of-band command line control. Telnet uses plaintext remote CLI over TCP port 23, while SSH encrypts remote CLI over TCP port 22. HTTP uses TCP port 80, while HTTPS encrypts web management over TCP port 443. TACAX Plus commonly uses TCP port 49, while Radius commonly uses UDP ports 1800. Prefer SSH over Telnet and HTTPS over HTTP. A cloud-managed platform places management through a cloud controller. In a wireless controller GUI, understand the workflow of creating a WLAN profile, selecting an SSID, mapping it to the correct VLAN or network, configuring security and QoS options, and enabling the WLAN. Exact screen layouts vary, so validate the relationships rather than memorizing pixels. Security fundamentals begins with precise terms. A threat is something capable of causing harm, such as an attacker, malware, fire, or insider. A vulnerability is a weakness, such as an unpatched server, weak password, exposed service, or bad ACL. An exploit is the method or code that uses a vulnerability, while a mitigation is a control that reduces risk. Effective programs combine technical controls with awareness, user training, physical security, policies, and procedures. Locks, badges, cameras, guards, and controlled server room access address physical exposure. Security is layered because no single control removes every threat. And operational discipline matters as much as installed technology. Secure local device access begins with protected credentials and local identity. Configure privileged mode protection with Enable Secret Strong Secret, and create an administrator with username admin privilege 15 secret another secret. Enter line console 0 and require the local database with login local. Enter line VTY04. Require login local, and restrict remote transport with transport input SSH. The Enable secret is preferred over the older Enable password. The command service password -encryption obscures certain plain text configuration passwords, but traditional Type 7 encoding is not strong cryptographic protection. Good policy also requires adequate length, unique storage, lifecycle controls, rate limiting, and avoidance of shared credentials. Multi-factor authentication combines different factor categories, such as something known, possessed, and inherent. Complete SSH setup by assigning hostname R1 and IP domain-name example.com. Create a local login with username, admin secret password. Then generate keys with CryptoKey, generate RSA, and require version 2 with IP SSH version 2. Enter line VTY04. Apply login local and permit only SSH with transport input SSH. Verify server status and version information with show IP SSH. Verify the VTY configuration with show running -config section line VTY, and make an actual remote connection from an authorized client. SSH encrypts management traffic over TCP port 22, while Telnet exposes plain text over TCP port 23. If SSH fails, check hostname, domain name, RSA keys, local user, VTY authentication, transport restriction, interface reachability, ACLs, and client compatibility. IPsec virtual private networks can connect sites or individual remote users. A site-to-site design creates an encrypted tunnel between gateways, so networks at Office A and Office B can communicate. A remote access design encrypts traffic from one user device to an enterprise VPN gateway. IK commonly negotiates security and establishes keys, while ESP commonly protects user traffic. At CCNA depth, focus on purpose, endpoint roles, and architecture, rather than deep cryptographic configuration. A tunnel does not automatically make every route or policy correct, so reachability, interesting traffic, identity, and access controls still matter. An IPv4 ACL processes access control entries from top to bottom, stops at the first match, and ends with an implicit deny. A standard ACL primarily matches source IPv4 addresses. Create one with access-list 10, permit 192.168 to 10.0.0.0.255, and traditionally, place it closer to the destination, because it lacks destination detail. An extended ACL can match protocol, source, destination, and ports. Create an HTTPS rule with access-list 100 permit TCP 192.168 10.0.0.0.255 host 10.1.1.10 EQ 443. That entry permits TCP from the 192.168.10.0/24 network to host 10.1.1.1.1. Extended ACLs are traditionally placed closer to the source to stop unwanted traffic early. Wildcard 0 bits must match, while wildcard 1 bits are ignored. The keyword host represents one exact IPv4 address and equals a 0.0.0.0 wildcard, while the keyword any represents all IPv4 addresses. Apply ACL 100 inbound by entering interface G0/0 and then IP access-group 100 in. Direction is always viewed from the router interface, so inbound traffic enters the router through that interface, and outbound traffic exits through it. Verify entries and match counters with show access-lists, and verify interface attachment and direction with show IP interface. Generate permitted and denied test traffic, run show access-lists again, and confirm expected counters increase. A zero counter can reveal wrong placement, wrong direction, wrong addresses, or traffic that never reaches the interface. DHCP snooping protects clients from rogue DHCP servers by classifying ports as trusted or untrusted. The legitimate server or uplink path should be trusted, while client access ports remain untrusted. Snooping also builds bindings containing MAC address, IP address, VLAN, port, and lease data. Dynamic ARP inspection uses trusted information, commonly the DHCP snooping binding database, to reject invalid ARP claims and reduce ARP poisoning. Port security restricts MAC addresses on an access port. Enter interface G0/1. Enforce switch port mode access. Enable the feature with switchport port-security. Set switchport port-security maximum 2. And learn secure addresses with switchport port-security MAC-address sticky. Verify with show port-security, interface G0/1. And inspect secure addresses with show port-security address. Port security violation modes are protect, restrict, and shutdown, with shutdown commonly serving as the default. Sticky learning records dynamically learned addresses as secure sticky MAC addresses. If a port becomes error disabled, identify the violation and authorized endpoint before recovery rather than simply bouncing the interface. DHCP snooping protects DHCP behavior, while dynamic ARP inspection protects ARP behavior, so they solve related but distinct attacks. AAA separates authentication, authorization, and accounting. Authentication proves identity, authorization decides permitted actions, and accounting records logins, commands, usage, and sessions. TakeAX Plus and Radius can centralize these functions, while local credentials provide a limited fallback or standalone method. Wireless security progressed from obsolete WPA through legacy WPA to WPA2 and WPA3. WPA is associated with TKIP, while secure WPA2 deployments use AES-based CCMP. WPA3 Personal improves the personal authentication exchange by using simultaneous authentication of equals instead of the traditional WPA2 Personal Pre-Shared Key Exchange. Enterprise Wireless commonly combines 802.1x with Radius for identity-based access. To configure a WPA2 Personal WLAN conceptually, choose the SSID, select WPA2, set the pre-shared key, map the correct VLAN or network, and enable the WLAN. A client needs the correct SSID, key, and compatible security settings. Never describe an SSID as a security control, and never preserve WEP or weak legacy modes merely for convenience. IP services starts with network address translation terminology. An inside local address identifies the internal host in the inside network, such as 192.168.1.10. An inside global address represents that host externally, such as 203.0.113.10. Outside local and outside global. Describe the outside host from internal and global perspectives. Although inside local and inside global receive the most CCNA attention. Mark the internal interface by entering interface G0/0 and IP NAT inside. Mark the external interface by entering interface G0/1 and IP NAT outside. Configure one-to-one translation with IP NAT inside source, static 192.168.1.10.203.0.113.1. Verify active mappings with show IP NAT translations and overall behavior with show IP NAT statistics. Dynamic NAT draws addresses from a public pool. Define the pool with IP NAT pool, public 203.0.113, 200320, 20320, net mask 255.255.2055.0. Match internal clients with access-list 1, permit 192.168, 1.0, 0.0.0255, and connect the ACL to the pool with IP NAT. Inside source list 1 pool, public. Port address translation allows many inside hosts to share an outside address by distinguishing sessions with transport information. Configure PAT through the outside interface with IP NAT inside source list 1 interface, gigabit Ethernet 0/1 overload, or add overload to an appropriate pool workflow. Generate traffic from inside to outside. Then, use show IP NAT translations to inspect local and global addresses and ports. Use show IP NAT statistics to verify inside and outside interfaces, hits, misses, and configuration. NTP synchronizes network device clocks, which matters for logs, certificates, troubleshooting, event correlation, and security investigations. Configure a client with NTP server 10.1.1.10. Then verify association and synchronization with the show NTP associations command, the show NTP status command, and the show clock command. DHCP automatically provides address, mask, gateway, DNS, and other options. Its DORA exchange proceeds through discover, offer, request, and acknowledgement, using UDP port 67 on the server and UDP port 68 on the client. DNS maps names to addresses and other information. An A record maps to IPv4, AAA maps to IPv6, CNAME creates an alias, and MX identifies mail service. DNS commonly uses UDP port 53 and uses TCP port 53 when required. A router interface can obtain an IPv4 address from DHCP, and activate the interface with no shutdown, verify the assigned address, and state with Show IP Interface Brief. Inspect learned routing with Show IP Route, and test the upstream gateway. DHCP relay is required when a client broadcast must reach a server on another subnet, because routers normally do not forward Layer 3 broadcasts. On the router interface receiving the client's broadcast, configure IP helper-address 10.10.10.10. Verify that the helper is on the client-facing interface with show running-config interface G0/0. Then test lease acquisition and confirm the client receives the correct address, prefix, gateway, and DNS information. SNMP uses a manager, an agent on the network device, and managed objects identified through MIBs and OIDs. Operations include get, set, trap, and inform. SNMP version 2C uses community strings and lacks modern strong security, while SNMP version 3 can provide authentication, integrity, and encryption or privacy. Prefer version 3 in secure deployments. syslog severity ranges from 0 through 7, with lower numbers indicating greater severity. 0 is emergency, 1 is alert, 2 is critical, 3 is error, 4 is warning, 5 is notification, 6 is informational, and 7 is debugging. Facilities identify the message source or category, while severity identifies importance. Accurate NTP time makes messages from multiple devices meaningfully comparable. Quality of service decides treatment during congestion, but cannot create bandwidth. Classification identifies traffic, such as voice, video, web, or backup. Marking records a class, with DSCP at Layer 3 and CoS in the Layer 2 802.1 queue field. Queuing and scheduling determine forwarding preference when traffic demand exceeds output capacity. Policing drops or remarks excess traffic immediately, and normally avoids large buffering delay. Shaping buffers excess traffic and transmits it later, smoothing the rate at the cost of delay. Remember policing as immediate enforcement and shaping as delayed smoothing. Choose behavior according to application needs, because voice is sensitive to delay and jitter, while bulk transfer can usually tolerate waiting. TFTP and FTP provide different transfer behavior. TFTP uses UDP port 69, has low overhead, and lacks ordinary username and password authentication, so it is suited only to controlled environments for simple image or configuration transfers. FTP uses TCP, supports authentication, and provides more capability. Traditional FTP uses TCP port 21 for control and a separate data connection. For device management, select the protocol based on security, reliability, environment, and server support rather than assuming all file transfers are equivalent. Verify source reachability and file integrity after any transfer. Automation and programmability closes the blueprint by explaining how repeatable systems improve network operations. Manually connecting to hundreds of devices is slow, inconsistent, difficult to audit, and prone to human error. Automation can apply desired configuration at scale with consistency, repeatability, speed, and recorded results. Traditional devices each run control plane logic and make many decisions independently. A controller-based design centralizes or logically centralizes policy and visibility, while infrastructure still forwards traffic. The control plane decides where frames and packets should go through mechanisms such as OSPF and STP, while the data plane moves traffic using forwarding tables created from control plane information. A software-defined architecture separates useful concepts into underlay, overlay, and fabric. The underlay is the physical IP network of routers, switches, links, and routing that provides basic transport. The overlay is a virtual or logical network built over that transport, often through tunnels between edge devices. The fabric combines underlay and overlay functions to provide automated connectivity and policy. From a controller's perspective, northbound APIs connect the controller toward applications, while southbound APIs connect it toward network infrastructure. North means toward applications, and south means toward devices. Centralized policy does not remove the need for resilient underlay reachability, because an overlay still depends on packets crossing physical links. Version 1.1 explicitly includes predictive artificial intelligence, generative artificial intelligence, and machine learning in network operations. Predictive systems analyze patterns to forecast failures, capacity, congestion, anomalies, or abnormal traffic. A rising interface error rate can support a prediction that a link is likely to fail. Generative systems create content from instructions and context, such as candidate configurations, log summaries, alert explanations, troubleshooting steps, or natural language queries. Predictive systems forecast or classify, while generative systems create content. Neither category is automatically correct. Engineers must validate inventory, syntax, intended state, security impact, test results, and device readback before accepting a network change. REST APIs expose resources through URLs or URIs. Read the collection with get/API/v1/devices. Create a resource with post/API/v1/devices. Replace resource 1 with put/API/v1/devices/1. Partially update it with patch/API/v1/devices/1. And remove it with delete/API/v1/devices/1. CRUD therefore maps create to post, read to get, update to put or patch, and delete to delete. Common success responses include 200 OK, 201 created, and 204 no content. Common client errors include 400 bad request, 401 unauthorized, 403 forbidden, and 404 not found, while 500 indicates a server error. A 401 normally indicates an authentication problem, while 403 means the request is understood, but the authenticated identity lacks permission. Authentication can use basic authentication, API keys, bearer tokens, or OAuth, depending on the API. Treat credentials as secrets. Use encrypted transport, check status codes, and verify returned state rather than assuming a submitted request succeeded. Ansible commonly performs configuration management, device automation, and repeatable operational tasks through YAML playbooks. It is typically agentless for network automation and can communicate through SSH or APIs. Terraform primarily expresses infrastructure as code for networks, virtual machines, cloud resources, and services. Terraform uses providers and maintains state information. A useful exam distinction is that Ansible commonly configures and operates systems, while Terraform commonly provisions and manages infrastructure, although real deployments overlap. Select tools by desired state model, platform support, idempotence, inventory, state handling, review process, and rollback needs, rather than by slogans alone. JSON represents structured data with objects and braces, arrays and brackets, and key value pairs. A hostname key can hold the string R1. An interfaces key can hold an array of interface objects. An enabled key can hold true or false. An integer can hold a number such as 100, and an absent value can be null. JSON keys and strings use double quotes. Objects group named values. Arrays preserve ordered collections. Booleans are lowercase true and false. Numbers are unquoted, and null represents no value. Read nesting carefully, because an address inside the second interface object is not the same field as an address at the document root. Valid syntax, valid schema, and operationally correct intent are three separate checks. Finish by combining the domains into one troubleshooting discipline. Start with the client address, prefix, gateway, DNS, and DHCP state. Then inspect medium, interface errors, speed, and duplex. Follow source MAC learning, destination forwarding, VLAN membership, trunks, Ether channel, and spanning tree roles. At layer 3, apply longest prefix, administrative distance, and metric in that exact order. Then inspect static routes, OSPF neighbors, and first hop redundancy. Continue through DHCP relay, DNS, NAT, ACL direction, and counters, QoS, and security controls. Correlate NTP, syslog, SNMP, controller, and automation evidence. Make the smallest justified correction, then verify configuration, control plane state, forwarding state, and end-to-end service in both directions.